Welcome to section 3, and in this particular section I'm going to talk about performance optimization in Athena. So the first thing is the storage level optimization. So as you already know that Athena reads records from data that is stored in S3, and there is no way that we can physically store the data in Athena cluster. So Athena cluster is nothing but a Trino cluster which is used only as a query engine, and the data would be stored in S3 always. So it makes sense that the storage level optimization plays a very important role in the performance optimization also. For example, it's better to use columnar file formats like Parquet and ORC. So why columnar file formats? Because let's say you have 100 columns and you are selecting only 10 columns out of it. If you use columnar file format, then the amount of data that will be scanned would be much lesser. Let's say the file size is 500 GB for 100 columns, and we are selecting only 10 GB, 10 columns. So considering 5 GB per column, it will fetch only 50 GB as opposed to 500 GB. So 500 GB for 100 columns, so each column would be 5 GB. So 10 columns would be 15 GB. Very simplistic example, just to make you understand how important it is to use columnar file format in query engines like Athena, Spark, Presto, Trino, etc. Then partitioning also plays a very important role. Why? Because as I have already shown you that if you partition the table, we put the files or folders in that particular partition, and we have to mention the partition column in the where clause. And if we do so, again, the amount of data scanned would be reduced drastically. So let's say you have 10 partitions and each partition is of size 50 GB, and you have columnar file format, and out of those columns you are selecting only few columns, then imagine the savings in data scan, which would translate to better performance, because again you are scanning only a single partition, and that too only a few columns in that particular partition. Same is the case with bucketing also. We have talked about bucketing. So what happens in bucketing is that the buckets are created by Athena. We mention the number of buckets. Let's say if the number of buckets is 8, then whatever rows we have, all those rows would be accommodated in those 8 buckets. And these 8 buckets would be created at partition level also. So let's say you have 10 partitions and you have mentioned 8 buckets, then each partition would have 8 bucket. But obviously there's a caveat that the clustered column or the column based on which we have done the bucketing has to be there in the where clause. So if you mention both the partitioning column and the bucketing column, so what would happen? It will first go and hit that particular partition, and inside of that partition it will only go and hit the bucket if we mention the clustered column or the bucketing column. Also, it's better to avoid too many files in a folder, and if you have downloaded the Parquet files and etc., you would see that there are a lot of files present in that particular folder. We should not do that. The number of files should be much lesser. Now, how do you do that? Basically, when you store the files in Parquet or ORC or Avro, we use processing layers like Spark, either Spark on EMR or Spark on Glue, to store the records in S3. So when we use that, we can actually reduce the number of files in Spark itself. So of course, I'm not going to talk about Spark here. So if you want to know about Spark and processing more, you can look out for my second video on data engineering, which is Data Engineering Volume 2. Okay, so that is the storage level optimization. So before going into further optimization discussion, let me reiterate or recap the architecture. So this is the Trino cluster. This is how the architecture is. You have coordinated node, and then you can have one or more worker nodes, and this communication channel between all the worker nodes and coordinator nodes. And what happens is that if worker node 1 gets certain rows, it might move those rows to worker node 2 or worker node 3 and so on and so forth, meaning that each of these worker nodes who are or will be doing the actual work can share or move data to each other or pass data to each other also. Now our data is sitting in S3. So what would happen? The Athena service, which uses Trino cluster, will read records from S3. So behind the scenes, these files would be broken down into multiple segments or chunks and then would be processed by individual worker nodes. So it's not that the entire file would be processed by a single node. So each node would get a segment of the file. Now, this is how the architecture looks like. Now, at each node, there can be multiple processing stages and there can be exchange of data across nodes also, depending on different join types, data scanning, etc. So this is again the architecture and the high level working of how Athena reads data and does the processing. So let's look at access plan, because this is how the SQL statement would be executed in your Athena cluster. So if you want to see the output of explain, you can run explain followed by the query, or explain analyze followed by the query. Now the difference between the two is that explain will just give you the access plan and explain analyze will execute the query, and along with that it will give you the access plan, and it will also tell you the actual execution time for each stage. The output format of explain can be either in text and JSON, and there are three types of rather explain output. One is logical, the other one is distributed, and the third one is IO. So what is logical plan? Logical plan is basically for the SQL engine, meaning that how the SQL would be executed on each of the nodes. So that is the actual access plan, and it is created by the coordinator node, and this access plan is basically sent to all the worker nodes. So that is the logical plan. We can get the logical plan by typing or by running the command explain followed by type logical and then the query. Then you have the distributed plan, and the distributed plan is how this logical plan would be executed physically in the cluster. Of course, I mean, we have coordinator nodes and worker nodes, etc. Now, how the data movement would happen across the nodes, at which stage the data movement would happen, etc., etc. So that's what the distributed plan is. And we can get the output of the distributed plan using this explain followed by type distributed and then the query or the SQL query. And IO plan actually tells you the data scan that is done from the underlying S3 objects. Now, before going further, let's talk about the explain operators, because we'll be looking at these operators in the hands-on. As I already mentioned, that the query execution is divided into processing stages or fragments. When the explain output shows single, it means that the processing stage is performed on a single node. So let's say we have three nodes. If we mention single, then the processing would happen in only one of the nodes. Then you have hash. So what hash does, the input data of a table is distributed across the nodes using hash function. And then the stage is processed. Again, the stage is coming from the logical plan, right? So let's say you have the table data in S3 and then you have a hash function. The records would be read, it would pass through the hash function, and then the records would be sent to these nodes based on the output of the hash function. Then you have round robin operator also. So if you see that there's round robin, it means that the input data is distributed across the nodes using a round robin fashion for that particular stage. So again, let's say we have three nodes and you have the table data in S3. So what would happen, that the records would be distributed in a round robin fashion. So the first record would go to node 1, the second record would go to node 2, then the third would go to node 3, so on and so forth. So this is round robin. And finally, there's broadcast, which means that the input data of the table is broadcasted to all the nodes. So the records are read and sent to all the nodes. Then you have another type of explain operators. The second one is data exchange, which means how data is moved across nodes. Then we have local exchange. And in local exchange, what it means is that the data transfer happens within the node itself. across different stages. As I have shown you that a single node can handle multiple stages, and if it is local exchange, it means that data is getting passed from one stage to another stage within that particular node only. Then you have remote exchange, which is of course data transfer across nodes for different stages in the query. So in this case, the records would be moved to multiple nodes or moved from one node to another node. Then you have logical data exchange also, which happens during logical plan. The first one is gather. So in this case, if you have aggregation like sum, count, sort, etc., a single node would gather output from all the other nodes and then send the final result set. Then you have repartition, wherein the data would be sent to a specific node based on the partition scheme that we mentioned. Then you have replicate also. It is similar to broadcasting, where the data is replicated or copied to all the nodes. Then you have distributed data exchange also during the distributed plan. So you have hash distribution and then you have single distribution. These are the only two distributions that we have. So single distribution means that the data distribution is happening to a single node, and in hash distribution, the data is distributed across multiple nodes using hash functions. And this is the final set of the operators that explain plan has. We have scans. We have table scan, which basically scans the table data. Then we have scan filter. So here the table data would be scanned, and then partition level and non-partition level scan or filtering would be applied based on the where clause. If the table is partitioned, then the filter would be applied on the partition column. If the table is non-partitioned, then also the filter would be applied on the scanned records. Then you have scan filter project, which is the summation of scan filter plus projecting the record. So if you select only let's say few columns, then those columns will be projected to improve performance in the later stages, or only the required columns would be moved to later stages. All the columns will not be taken. Then we have table joins, which are very straightforward. There are no internal joins as such. So we have cross join, inner join, left join, a right join, and full join. So these are the table joins that are performed. Then we have join distribution using partitioned. So let's say we are joining two tables, and Athena always joins two tables, and the result set is joined again with the third table. You have two or more table joins. So two tables are hash partitioned across the nodes. Then you have replicated, wherein one table is hash partitioned across the nodes and the other table is replicated to all nodes. So again, as I said, right, so if you have joins with multiple tables, so let's say four tables, the first two table would be joined, then the result set would be joined with the third table, and then the result set of that output would be joined with the fourth table. So always two tables are taking part in the joining operation. So in the first case, in the partition case, both the tables would be hash partitioned across nodes. In the second case, only one table would be hash partitioned and the other one would be copied to all the nodes.